I will just continue with what I had left off before I go to this story of ratio test. I will just want to remind you that if this summation n converges, then limit of n goes to 0. This is a simple thing, you can figure it out yourself. But if limit of n goes to 0, then summation n need not converge. So, an example is summation 1 by n. So, limit of 1 by n goes to 0. So, but summation 1 by n does not converge. So, let us now look at another more test. It might be slightly boring that we are just doing test after test, but these are useful because every series cannot be checked up in the same way. So, again you have a sequence summation n of positive terms, then you have to find, that is why it is called the ratio test. You are looking at the rate of the movement of the sums by looking at the ratio of the terms. So, suppose this is rho some number. If rho is strictly less than 1, then summation n converges. Number 2, if rho is greater than 1, then series diverges. Number 3, if rho is equal to 1, then the test is inconclusive. Then you have to look for other tests or other methods to show convergence if you think there is a convergence, or show divergence. So, you can't make any conclusion. So, let us try out an example that will show us using this test that this is an effective test. We can at least check out. So, you can write, so you are asking for a sum of this or whether it converges. So, the first step is writing n plus 1 by n, and that is so again you will have n plus 1 by n is equal to 1/3 in by so divided by 2n. So, it is 2 plus 5 into 2 to the power minus n on 5 by 2n, that is 1 plus 5 into 2 to the power minus n. So, ultimately the limit of, so this limit, so 1/3 is outside, sorry. So, limit of n tends to infinity 1/3 2 plus 5 by 2 to the power n 1 plus 5 by 2 to the power n, this is nothing but 2/3 because this goes to 0. The 5 by 2 to the power n part goes to 0. So, it is 2/3. So, 2/3 is strictly less than 1. So, which means now that summation n converges. But note that 2/3 is not really its sum, it is just this number rho. How do I find the sum of this? Actually, finally say what is the sum. So, the sum now, because this series is convergent, immediate all the parts itself has to be convergent. So, I can break it up into two parts. So, I can actually write this as five is a common number, so it can be taken out. So, if you look at these two part series, this is what is called a geometric series, because the first term of this series, sorry, n equal to n has been 0, it does not matter. So, when n equal to 0, it is 1, when n equal to 1, it is 2/3, then 2/3 square. So, you are multiplying with every number 2/3 and getting the next number, this is called a geometric series. So, how to sum a geometric series? So, geometric series is of the form So, now if I look at Sn of a geometric series, where A, this R is called the common ratio. A is the first term, because if I divide A any term by A, if I make An plus by An, then I will simply have R. So, two ways of looking at this. Now, let me consider the case of geometric series where R is strictly less than 1, basically series of this form. Here R is 2/3, here R is 1/3. So, here you will have A, so A plus AR plus ARN. Then this is nothing but A into 1 minus R to the power n plus 1 divided by 1 minus R. Now, limit of Sn as n tends to infinity is what? It is as n goes to infinity, because R is strictly less than 1, this goes to 0. So, it is finally, so this is since R to the power n goes to 0 as n goes to infinity, since R is less than 1. Of course, here we are taking the common ratio R to be strictly greater than 0. You can also use in this particular case, where if A is a positive term, here we are really not bothering about A being a positive term, but here if you consider A also is a positive term like here, then you can actually do the ratio test, because An plus 1 by An here is nothing but R, and if you take limit n tends to infinity, this is also going to give you R, and R is anyway strictly less than 1. So, you can guarantee that it converges, but here you know that this summation n equal to 0 to infinity ARN. So, this is nothing but A into 1 minus R. So, similarly, so you apply this here, so what you will have? The first term is 1, so it is 1 by 1 minus 2/3 plus 5 into the first term is 1, so 1 by 1 minus 1/3. So, it is 1 by 1/3 is 1/3, so it is 3 plus 5 into 3 by 2, it is 3 plus it is 15 by 2, so it is 21 by 2. So, that is the final conclusion. Now, there is some other test called the ratio root test. So, let us see, let us do the root test. So, you take again a series of positive terms, Once I take this term, and what I do, I take the nth root of the nth term, then I take the limit as n tends to infinity, and suppose this is rho. Again the same thing as the root test, rho strictly than the 1, it implies summation n converges, rho greater than 1 implies summation n diverges, rho equal to 1 implies test inconclusive. So on we have this information. So now how do I make a check, right? How do I check it through the root test? Suppose when you do root tests are done when you have powers. When you have powers on your terms, then your root becomes useful. Say you have nth power in the nth term, then your root term test becomes useful. So various tests, they are designed for handling various types of series. For example, if you look at this one, what happens to this? So an here is n square by, implies a root n, nth root of n here is n to the power 2 by n divided by 2. If I take the limit n to the power 2 by n divided by 2, n tends to infinity, what happens? N becomes bigger, but 2 by n goes to at 0. So how? So basically whatever, how large your number is n, if 2 by n is going towards 0, then finally the number has to stabilize towards 1. So basically the limit of this is half, and this is less than 1, and hence we conclude that this series converges. Okay. So why we have just spoken about sequence of positive terms. What about if you have a sequence of alternating terms, one term plus one term minus, one term plus one term minus, what will you do? So for example, you take the alternating harmonic series as an example. So let us see alternating harmonic series, it is a very interesting thing which happens here. So in general, an alternating series is given in this term. Instead of an, we will write the terms as un. It is u1 minus u2 plus u3 minus u4, so and so forth. What is the meaning of convergence? The convergence again is same. Take the sequence of partial sums and see whether they converge. But here you cannot guarantee increasingness of the sequence of partial sums, that is the problem. So if you cannot guarantee that, then is there any way to test it, test that the sequence actually converges? Basically, can you then test under what sort of conditions the limit of the partial sequence of partial sums converges? So one of the most basic tests that you take for this alternating series is called the Leibniz test. Remember, in those days people had thought about these sort of ideas. So it's, people get confused even nowadays with these ideas. In those days, so at those days this was actually very advanced research mathematics which we are learning at this very simple basic stage. So you have given now suppose the following holds. All the UNs, these U1, U2, U3, so there is a sign in before them, does not matter, all the UNs are positive. 2, UN is greater than UN plus 1 for all n greater than or equal to n naught, some n naught, some n naught. So basically UN, the this un itself has to form a decreasing series. If I just take out this u1, u2, u3, u4, it will form a decreasing series, and third un goes to 0. If all these things happen, we will conclude that summation converges. So, let us now test it for the alternating harmonic series example itself. The alternating harmonic series example, of course, the 1 half, 1/3, 1/4, 1/5, they are all positive terms. Second of all, un is bigger than un plus 1. So, 1 is bigger than half, half is bigger than 1/3, 1/3 is bigger than 1/4, and so forth. un goes to 0, that is does, and here 1 by n goes to 0. So, straight it goes to 0, finished, that game is over. So, by Leibniz test we can conclude that it converges. There is something very interesting about how to show that whether alternating series converges is to use the idea of what is called an absolutely convergent series. Absolutely convergent series is, so you take a sigma summation a n. So, it could be an alternating series, I am not writing the detail, it could be an alternating series. But if and here a n could be positive, negative, anything, but now here when you take the mod of a n, they are all positive terms. So, then if this sequence, but if this converges, then n equal to 1 to infinity, then we say that, and we say summation a n absolutely converges. But there could be an alternating series which need not absolutely converge, but just converge by the very basic definition of convergence. Such a series is called a conditionally convergent series. An example we had already given in the starting. See, if you look at the alternating harmonic series, and what is this, what is summation mod of u a n here? It is 1 plus half plus 1/3 plus 1/4, etc. So, that will give you the harmonic series, right. So, harmonic series is divergent. So, this series, alternating harmonic series, is conditionally convergent by is convergent by Leibniz state, but it is not absolutely convergent, because if you make summation a n here, so basically for the harmonic, in this particular case if you take the mod of, and this is nothing but so, but this series does not converge, we have already shown, that is there is a harmonic series. So, this is an example of a series which is convergent but not absolutely convergent, which is called conditionally convergent. So, any series which is convergent should be conditionally convergent. So, if a n absolutely converges, it implies that summation a n converges, but it is not so simple to show this fact, it needs a little. So, this is absolutely converging, this is summation mod a n is converging, but that means summation a n also converges. We do not prove it, it is but it is not a straightforward fact. So, now observe this particular alternating series, 1 plus half plus 1/4 minus 1/8 and so forth. So, so look at the series. So, this is summation a n, this is a geometric series basically when you write summation mod n. This is 1 plus half plus 1/4, that is 1 by 2 square 1/8. So, in fact it has a sum 1 by 1 minus half, the sum is 2. So, here summation mod n converges, so a n also converges. So, this is called a, so a n is an absolutely, so this is an example of an alternating series which is absolutely convergent. So, we end our second talk here. The third part of infinite series would essentially we would be bothered about something called power series, and rather we would be not getting too much into the details of power series, but going largely into the issues associated with Taylor's theorem. So, how do we represent a Taylor's theorem as a power series? That would be our goal in the next chapter or next section. So, that will be lecture 3, which will start after some time, the next lecture, in which we will talk about the series representation of functions, and where Taylor series will come, where you basically make the Taylor polynomial into a series. Thank you very much.